Continuous integration in SoC design, challenges and solutions. This paper introduced the implementation of continuous integration in large-scale system-on-chip SoC design. We discussed the challenges encountered, our solutions, and the resulting automated CI system for SoC design and verification code. Our approach leverages both modern continuous integration practices in software development and high-performance computing HPC environment and existing regression scripts commonly used in chip design and verification, enabling the implementation of a user-friendly yet powerful continuous integration system. 1. Introduction. Continuous integration, CI, as a practice that allows developers to frequently integrate code changes into a shared code repository and perform the automated builds and tests, has gradually been applied in the hardware development field. Although many companies has introduced continuous integration into their chip as on system-on-chip SoC design and verification workflows, implementing an efficient hardware continuous integration system still faces many challenges due to several differences between hardware and software development. These challenges are mainly reflected in the following aspects. First, the chip design and verification rely on job scheduling systems on high-performance computing HPC environment to handle build and simulation work, and this unique infrastructure and workflows are not compatible with a mature continuous integration tool. A common approach to address this issue is to configure additional dedicated computing resources for the continuous integration system. However, this solution faces a dilemma. If additional resources are limited, it becomes difficult to run automated tests on a large scale in parallel. If a large amount of computing resources is added, it leads to excessive cost. To resolve this dilemma, there have been some attempts in the industry, some running tests once at scheduled time, some combining multiple merges to run tests once, and some saving code merge events to a queue and running jobs one by from the queue. But these solutions more or less have problems such as poor real-time performance and system complexity. Second, many modern continuous integration tools are deeply integrated with Git or even developed directly based on Git. If the Git is not used, some basic components need to be developed independently. We choose to adopt popular tools from the software field as much as possible instead of reinventing the wheel, which not only allows us to continuously follow the latest concepts and methods in the field of the continuous integration, but also minimizing the custom development and maintenance costs, avoiding the need for a dedicated maintenance personnel. However, using Git for chip design code management brings new problems, including performance degradation in the large code repositories, binary file merge conflicts, and large file development management challenges. These problems do not exist or not obvious when using Porthos or Subvision. For example, Porthos is very efficient and powerful in supporting large repositories and large files, both Porthos and Subversion supporting binary file locking. To implement a continuous integration system that is both easy to use and powerful, we connected the continuous integration system with the HPC environment, clusters, and special compute nodes and storage to allow jobs to run in parallel, allowing the use of HPC computing resources in the continuous integration and efficiently utilizing them. In the early stage of the chip development, when regression testing has not yet begun, HPC resources are not fully utilized, while the CI system requires a large amount of HPC. As development progresses, code merge decays and CI demand decrease, but large-scale regression testing begins to start up, requiring more HPC resources. This complementary scheduling makes the implementation of CI possible without additional HP resources, even if the continuous integration system is designed to perform automatic tests before and after each code merge. This way, the continuous integration system will be simpler to use Git smoothly for code management in large SoC projects. We upgraded our IT infrastructure, changed the topology of the code storage and access, and implemented a series of the special Git configuration and method, which will be detailed in subsequent sections. Chapter 2: CI System Architecture. To implement CI for SoC design verification, first, there must be a set of built-on simulation scripts that can provide parameterized commands to start the build and or simulation of different tests. The CI system will call this script to implement the automatic testing function. For example, running sim-ba_test will compile the design and verification code responding to a test and generate an executable file, and the sim-sa_test can run this simulation. If it ends normally, the simulation passes and the exit code of this command is 0. An exit code of non-zero indicates task failure. The CI system will determine whether the test passes based on this exit code and display it in the user interface, thereby deciding whether the code should be merged. Most companies may already have similar tools, generally called regression scripts. On this basis, the following components are also needed. Figure 1. Basic component of CI flow. Moving forward, I will outline the capabilities of each component and suggest some viable tools for each. In the subsequent chapter, I will introduce our choices as well as more details. Version control system, VCS, storing chip design code, verification test cases, and configuration files. Webhook trigger automatically triggers CI process after code submission. Branch strategy management, supports feature main branch workflow, implement code merging and code reviews integration, such as GitLab, Bitbucket, and Git, and Azure repo, and etc. This article only focuses on workflows using Git for code management. Non-Git version control systems are not listed. Continuous Integration Platform, CI platform, providing a pipeline script for the user to implement, executing test pipelines, job monitor, real-time monitoring of verification task status, displaying the process of command execution in real time on the web page, including the complete output, pipeline execution. CI includes an agent or runner that executes command in the pipeline script, generally needing to be installed on separate hosts to clone the current branch code to verify that after the automatic test is triggered, and execute commands in the pipeline such as sim-b a_test, reporting result, notifying the VCS whether it can be merged, and promptly notify relevant personnel or verification results. Continuous integration platforms include GitLab CI, Bamboo, and Buildboot, and Jenkins, Azure Pipelines, and etc. Job scheduling system. Each pipeline will produce multiple jobs that need to be run in parallel. These jobs will be handed over the job scheduling system, managing and distributing to HPC, such as Slurm and LFS and PBN and etc. The command adapter connecting CI system and job scheduling system, handling the gap between the CI system and HPC system, including storage structure, user permissions, and etc., and converting CI platform command such as sim-ba_test into command required by the job scheduling system, such as srun-n sim-b a_test, such as Jacamar CI for GitLab, and or develop your own based on the CI system and job scheduling system used. So the HPC, using the original existing HPC. This way, the basic workflow is as follows. 1. Developers submit code to the version control system. 2. The webhook of the version control system triggers the CI pipeline. 3. CI platform parses the configuration, prepares the verification environment, and the CI learner agent clones the code of a current branch. And 4. Command adapter convert to test tasks into HPC jobs. 5. The scheduling system allocates jobs to appropriate compute nodes. 6. HPC executes verification tasks and return results. Results are returned through various levels back to the CI platform. As described in the above process, each pipeline run needs to clone the code once. The response speed of Git command is very critical. In many IC design companies, users working directories mounted network drives through the NFS or other network file systems rather than real local hard drives. Using Git to clone code and execute any Git commands in such working directories will have serious performance issues. So if the Git is used for version management, it must be ensured that the user's Git repository is stored on local hard drive of the host executing Git commands. To meet the Git requirement for local hard drives, we upgraded the IT infrastructure. 2 servers are needed, one for installing the version of the control system, such as GitLab, and one for installing the CI learner, such as GitLab runner, command adapter, such as Jacamar CI, and a job scheduling system with the final command executed on the HPC of the server cluster. So our hardware system became like this. Figure 2 is a hardware topology of a CI flow. So the Git server and CI learner, as well as the user work server, all have their own local storage for storing Git repositories locally. Among them, the local storage of the CI learner and the user work server needs to be shared with other public storage file servers through the network file protocols such as NFS to form the shared file system of several clusters. Of the server cluster. So because the server cluster needs to use the code of the CI runner and the user work server for build and simulation. So they need to be mounted on the server cluster, as shown by the solid arrows in the figure 2. The dashed arrows and the figure presented directly using Git clone or push code through Ethernet to synchronize between the local Git repositories and the Git server. And this way, it not only utilizes the high-performance computing capabilities of the server cluster, but also meets the requirement of Git repositories for local hard disk storage. Chapter 3 is the CI process to ensure the main branches is always available. Our main goal is to ensure that the main goal code mainline code always has no basic errors and maintains a known good state. To achieve this, our strategy is to automatically run a set of the tests before each code merge, only merging into a main line if all tests pass, and then the running this set of the automatic tests again after merging into the main line to ensure the correctness of the code after merging. This set of tests is called CI tests, covering multiple build and simulation at IP, subsystem, and SoC levels to ensure the basic functionality of all components. Multiple users can trigger CI tests simultaneously, and each CI test contains multiple build and simulation tasks that need to be executed in parallel, thus requiring a large amount of computing resources. The biggest benefit of executing CI tests vary every time code is merged into the main line is the rapid discovery of the errors. Developers can fix errors while their memory of the errors is still fresh, reducing the workload of task switching and review. At the same time, most bugs are fixed before they spread to others, thus reducing the workload of more people debugging due to the bugs spreading to other engineers. To automatically implement the process, we designed the following workflow. Figure 3. Workflow for design and verified based Git. So the all work starts from the main branch and main branch and while returning the main branch does not accept code pushes by default, only accepting merges. Before RTL freeze, only one long-term branch main is maintained. Whether design engineers or verification engineers, each time a feature is added or a bug is fixed, a new branch needs to be created. This branch is only for one person's use. And to complete the merge design main branch's timely manner, the planned workload for each branch should not be too large. So after completing work locally, push to your remote branch can push multiple times, then open a merge request on the web page, which automatically triggers CI tests. CI test jobs include two types. One is build and the other is simulation. One build may corresponding to more than one simulation, verifying the different functions through different simulation options. At the beginning of the test, all build work will be carried out in parallel. Each build will have its own separate directory, and if this build corresponds to a multiple simulation, a new subdirectories will be created within the directory for each simulation. Build will use the HPC through the job scheduling system as soon as the current will build ends or the simulation corresponding to the current build begin in parallel, also using HPC through the job scheduling system. Each build and simulation is treated as a separate job, and the output result will be returned in real time to the web page of the Git server, such as GitLab for easy debugging. After the job ends, the execution result, pass or fail, of the all jobs be summarized together. If even one does not pass, the current branch cannot be merged into main branch. At this time, the author needs to find the region and push the code again. Otherwise, it can be merged into main branch. CI tests are automatically triggered after pushing the code again. So it should be noted that before pushing code, developers should perform a Git rebase main operation locally, so that the push after merging the latest main branch code to maximize avoiding automatic test failure after code merging. The CI tests are automatically triggered again after the code is merged into the main branch, because merging may cause test passes on the own branch to fail, although the probability of this happens is small. At the same time, doing this can also promptly discover the problems in the main branch and promptly understand which merge brought about the problem. To speed up the turnaround, automatically trigger tests do not dump waveforms, but for some failed tests, it may be difficult to analyze region just through logs and waveform dumps are needed. In CI tests, including when the job scheduling system submit executed without identifying the person who triggered the current continuous integration pipeline, and the generated file's owner is also current trigger. The way, if the automatic test failed, the trigger can go to the directory of the failed automatic test case according to the directory displayed in the log, and use the build target files already generated by the automatic test to start the simulation with the jump parameters, thus saving the work and time of rebuild. Using the identity of the trigger to submit jobs through a job scheduling system has another advantage. Large chip design of the design companies generally allocated different HPC resources to different teams and limit the number of jobs running simultaneously. Submitting with the trigger identity can keep the use of the HPC computing resources within the company's policy requirements. So in chip verification tests, some variables in some tests will obtain values randomly, which may be different modes, switches, and etc. This way, the test may pass once with the same code but fail another time because it randomly got another mode, and etc. Thus, tests triggered by the merge requests by might be passed, but test triggered after merging into main may fail again. To ensure the reliability of a CI test result, specified random seeds were used in all CI test cases. So in actual time work, some multi-person collaboration problems may be encountered. For example, a feature design has been implemented and there is a CI test that automatically tests it every time the code is merged. Now the design engineer needs to change this design, and if the verification code is not modified accordingly, the test will inevitably fail, and the DE has no obligation to modify the verification code. The automatic test failed, so the design code cannot be merged. At this time, a Git feature called cherry pick needs to be used as long as the DE pushes the code to his remote branch. DV verification engineer, DV design verification engineer can get the DE's code through cherry pick on DV's local branch, thereby merging the DE code into main. Of course, Git will smartly handle different code authors and modification codes, and there won't be problems like these code being modified by DB. Chapter 4: CI Implementation based on a GitLab. After comparing multiple CI tools, we chose GitLab as our Git server, GitLab CI as the Git CI platform, and Jacamar CI as the adapter. We didn't choose the commonly used Jenkins Regression Manager tool mainly because it's more complex and even requires dedicated maintenance personnel. Jenkins uses a groovy Jenkins file to write pipelines, while GitLab CI, Azure DevOps, and GitHub and etc. all use YAML, making GitLab CI easier to use and maintain. The recent discussions among the developers on platforms like Reddit suggest that GitLab CI has been increasingly admired as a CI and CD tool in the recent years. GitLab CI and GitLab as a whole have very well integrated functions requiring no development on our part. Additionally, GitLab has an open-source third-party adapter, Jacamar CI, which solves the issue of connecting the HPC and supports multiple job scheduling systems such as Cobalt, QSub, LSF, BSub, PBS, QSub, and Slurm HPC. These components can help us implement an easy-to-use automatic testing process with very little code, and they are all open source and free. We use the community, version of the GitLab, which can have saved a lot of cost for the company. The data flow over the entire system shown in Figure 4. Figure 4 is the CI implementation data and data flow. So after users push code from their code repository to the remote branch, triggering a merge request, GitLab will automatically notify the GitLab runner to clone the code of the trigger branch. The cloning location is configured by us in Jacamar CI, a directory of the runner local disk named the current pipeline ID. Jacamar CI will submit jobs to HPC, and HPC will run our modified regression script. The parameters of the regression script specify whether it shall build or a simulation, which test it is. The command line output result of the build or a simulation will be returned to the GitLab to a web page in the real time for each debugging. After regression script execution is complete, if the exit code returned by the script is non-zero, if indicated an error occurred during the run, and GitLab will display the current test as a fail. If the scripted exit code is 0, it indicates the current test passed. After the pipeline is successfully executed, the cloned code and build artifact produced by the CI test are no longer needed. So we have a timed script executed as a root user that deletes directories older than 24 hours every day at noon. The other generally because our GitLab web page displays complete log, continuously accumulating log files will occupy a lot of storage, which also needs to be deleted periodically. So A. Customize your regression script and implement a CI script. Our regression script is a Python-developed tool used for building and simulation test cases. It can regress many test cases at once, but in the CI process, it is used to run a test for individual cases. For example, if we need to build and run test code named example underscore test underscore A, the command is sim-t example underscore test underscore A. If the build and simulation path the exit code is 0 or otherwise it's non-zero, GitLab CI relies on this return to code to determine whether the current test has passed or failed. Before simulating a test, we must first compile to generate an executable file, which we call a build. This build has its own file list and unique UVM underscore test, as well as all options needed for the build. Suppose there is a build name example underscore build. Under this build, multiple tests can be generated by setting different simulation parameters, sim options, and let's assume that in addition to example to test underscore A, there is another test called example underscore test B. So our regression tool supports executing the build and the sim simulation separately. We can compile and generate executable files using sim-b example underscore build and simulate based on the previously compiled executable file using the sim-t example underscore test underscore a minus the SO. So different simulation options are managed through YAML files with each test corresponding to different simulation options. After running the regression script, it will automatically parse the simulation options corresponding YAML files to generate simulation command. Build options are also stored in the YAML files. Figure 5 is a simple YAML file showing the one build and two tests. This is YAML 5. As figure 5 is YAML used by the regression script. The TB underscore path key value pair determine the folder of the current build, which contain the test bench file and design and verification file list for the current module, sequence for the current module, test cases file, and so on. Each module has such a build, and when the regression script is run, it created subdirectories for each build, and within the build directory, it created the simulation directory for each test, allowing for a parallel build and a parallel simulation. In this example, there is a tag key value pair. When the script is used for regression, the comment sim underscore bar tag and sanity minus tag sanity will compile and simulate the parallel all cases that contain the sanity tag. The CI process does not use this command. Each build and simulation needs to be submitted separated to the HPC, and the simulation job must wait for each corresponding build to succeed before it can be submitted. So it isn't necessary to generate dependencies between the build and the simulation. For this, we added the command sim genc minus tech ci genc ci take ci or genc tag, the regression script. The command generate build and simulation command for all test cases that include the CI tag and output them in a format of the GitLab continuous integration script appearing in individual jobs built-in dependency. We use GitLab CI's parent child pipeline mechanism to generate child pipeline script containing build and sim command and complete the CI test in the child pipeline as shown in figure 6. Figure 6 is a GitLab CI and enhanced regression and script implementation. B. GitLab Learner and Jacamar CI configuration. GitLab Learner provides a configuration called Custom Executor, which allows users to implement their own executor. We took advantage of this feature and specified the Jacamar CI as the executor and the learner's configuration file and etc. GitLab Learner configuration TOML. And the Jacamar CI configuration file, setting custom build directory to true allows the CI when run to obtain the pipeline ID from the current pipeline via CI pipeline ID. Create a new directory, clone the code, and simulate. The executor is used to specify the job scheduling system and setting the group permission to true allows users the same Linux group to view each other's logs to waveform. Chapter 5 Challenges to the using a Git in SoC project. Without any adjustment, simply using a Git directory can indeed encounter problems, as the number of files in repositories increase and the execution of the Git commands will become very slow. Git requires checking out the entire repository before modifying and committing, but actually some people's work only involves one or two directories. Git manages large files, and the historical version of large files will always exist in the Git repository. After modification and submission, the size of repository grew exponentially, so the Git merge cannot resolve the conflict of the binary files and does not have a locking feature like SVN. So the first problem has caused us a lot of trouble for a long time. This main reason has been mentioned before. That is, the location of the Git repository needs to be switched from NFS to local hard disk. In fact, we have completely lost of the feelings of the command latency after making this one just. If the repository is still large and there are performing problems, you can use the Git scalar and a sparse checkout to further optimize. It will further explained below. The second problem indeed exists in the historical version of Git, but Git 2.38 and later support the scalar command, which supports sparse checkout can set the directory to the checkout. To be checked out. So other directories will not appear on their own disk. Moreover, the scalar will obtain the storage object of the remote branches regularly in the background. It's almost real time when users use commands such as git fetch or git pull. Regularly, a scalar is a series of upgrades developed by Microsoft for managing large repository with Git. It was born out of the Microsoft production solutions for many years and was merged into the official Git repository in version 2.38. And very simple to use, just to replace the git clone command with a scalar clone. The third and fourth issues can be perfectly resolved using the same tool with tools that comes with the Git LFS, Git LFS. Git LFS allows large files to be stored in the proprietary directory specified by GitLab. In the Git code repository, it only stores the index of a large file and checks out a version that needs to be used only when it is used. Popular mono-repo recommends managing all project-related code in one Git repository, but it is more appropriate for third-party binaries of third-party libraries used in IC design to place outside the repository to reduce the size of the repository, such as network disks mounted by NFS. At the same time, the maintainer file list containing the version path of the third-party library in the Git repository. After the third-party library is updated, you can see the version change history in the Git repository. As for the merge conflict or binary files, LFS supports locking and unlocking, which is very convenient to use. Chapter 6 is implementation in a real project. The CI pipeline consists of 19 different test-batch builds and 23 simulation jobs, completing within an hour. While traditional manual integration and testing a similar project typically require 1 day per cycle, At peak of development, up to 40 pipelines were triggered daily, with 7 to 8 pipelines running simultaneously. Figure 8 pipeline starts last year. Throughout the 15-month development period, our team of 41 developers performed 3,303 merges, triggering 8,213 pipelines with 6,743 successful completion and 1,344 failures. The CI system demonstration significant improvement in bug detection and resolution efficiency. Developers typically identify the root causes within 5 minutes of a CI failure, compared to over 30 minutes in traditional flows, with some cases extending beyond the 24 hours. Based on historical data from previous projects using traditional methods, where each integration is consumed an average of 2.5 hours, half an hour, and 1,344 early code failures represented over 3,360 hours of saved engineering time. 7. Conclusion. We utilize the GitLab CI combined with our customer regression, script, and configuration, leveraging the existing HPC system to implement a lightweight and a different efficient CI system. Unlike a traditional CI system, and they require extensive custom AP or resources, our approach uniquely optimizes the use of existing HPC infrastructure, making it particularly suitable for large-scale chip design projects. This system demonstrates the following advantages: rapid error detection, allowing developers to fix the issues while their memory of the code is fresh. Reduced bug propagation, as most bugs are fixed before spreading to other team members. Maintaining the integrity of the main branch, ensuring that the main branch is always in good condition. All basic features test CI test have always passed. Optimize HPC utilization, eliminating the need for additional hardware investment. And this system significantly enhances our development process, enabling faster iterations and more reliable outcomes, and facilitating early detection of issues and reduce the overhead of manual testing and integration. Today I read this paper, Continuous Integration in SoC Design, Challenges and Solutions, from DVCON 2025. Thank you for your time. See you next time.